13.8 billion years ago, the universe began as an infinitely dense, incredibly hot speck that burst into a rapid expansion of space and time. Standard physics suggests that an outward explosion should eventually lose its momentum. On Earth, we expect friction or air resistance to sap energy from a blast, eventually bringing the debris to a halt. Physicists applied this same logic to the cosmos, identifying gravity as the ultimate brake. The combined mass of every galaxy and star in existence should exert a constant inward pull, fighting against the initial expansion. For most of the 20th century, the scientific consensus held that this gravitational drag was winning. Astronomers focused their research on calculating exactly how much the universe's expansion was slowing down. In 1998, two teams of astronomers used the Hubble Space Telescope to measure the distance of Type Ia supernovae. Because these exploding stars have a highly predictable luminosity, they serve as standard candles to gauge how far light has traveled across the cosmos. When the teams plotted their data, they found that distant supernovae were significantly fainter than their redshift predicted. This dimness meant the stars were much further away than established mathematical models allowed. Comparing the light's redshift to the actual distance, astronomers realized the expansion of the universe must have increased its speed while the light was in transit. Gravity had failed to slow the universe down. Instead, an unseen force had taken over the expansion, forcing galaxies apart faster and faster every second. To understand why the brakes failed, we have to look back to the early universe, when gravity actually was the dominant force. 9 billion years ago, the universe was physically smaller and much more crowded. This proximity gave dark matter, the invisible substance that makes up most of the universe's mass, an overwhelming gravitational advantage. Dark matter formed a massive structural web, exerting enough pull to overcome the expansion and draw hydrogen gas into dense pockets. These junctions became the birthplaces of the very first stars and galaxies. During this first era of cosmic history, the density of matter was high enough that gravity functioned exactly as predicted. The expansion of the universe was actively decelerating. However, as galaxies formed and moved, the spaces between them grew. Massive voids opened up, filled with nothing but empty vacuum. Empty space possesses an intrinsic vacuum energy, known as dark energy. Unlike matter, which thins out, dark energy remains constant. As the universe expands, it creates more empty space, providing more dark energy to drive even faster expansion. Approximately 5 billion years ago, the universe reached a tipping point. The expansion had created so much new space that the outward pressure of dark energy finally eclipsed the concentrated gravitational pull of dark matter. The inward pull of the cosmic brakes was finally overtaken by the expanding volume of the vacuum. Today, we verify this with the cosmic microwave background. Observations from Planck and WMAP satellites measured temperature fluctuations to determine the universe's geometry. This data confirms a flat universe, requiring dark energy to balance the total budget. These measurements reveal that dark energy accounts for roughly 68% of everything in our universe. This energy density represents the dominant component of the cosmic energy budget. It outweighs all dark and visible matter combined, providing the primary force that drives the current expansion rate of the cosmos. Because dark energy scales with the volume of space, there is no known mechanism to stop this runaway acceleration. The universe will continue to expand at an ever-increasing pace. In 100 billion years, the speed of this expansion will carry all galaxies outside our local group beyond the reach of their own light. A moment of wonder. A future observer will find a universe wiped clean of neighboring galaxies. The vibrant night sky will gradually fade into a permanent, lightless black. The Big Bang sparked the universe into existence with a flash of heat and energy. Dark energy ensures its end is a slow transition into the absolute cold and silence of the Big Freeze.